Okay, so I want to I want to go over this worksheet with you because it's got a whole bunch of different stuff, and I'm worried that you're not going to ask questions about it. So I'm gonna just go through with it. Okay, so here it says sketch the graph of the derivative of each case. So this is a linear equation with a negative slope. That looks like 0, 0. I go down to over 1. So my slope is negative 2 here. In fact, my slope is negative 2 everywhere here. So I draw the line y equals negative 2, and that's the derivative. Okay, now what about number 2? Well, remember, we start with planting the zero slopes, and I see very positive, less positive, heading to 0, 0 slope. So that, and then over here, 0, a little negative, much more negative, very negative, and so we get this. I'm aided in drawing this line because I know that my derivative of a polynomial is always 1 degree less. So here I see a negative x to the second, and so my derivative would be some kind of negative x to the first. Okay, how about this one? Well, again, I'm going to plant those zero slopes. I see a third degree polynomial, which suggests to me that my derivative is going to be a second degree polynomial. I see a positive leading coefficient, so my second degree polynomial I expect to go up, but let's see if that makes sense. From here to here, I see negative slopes, more negative slopes, that's about as negative as I get, and then less negative slopes back to 0. Over here I see only positive slopes that get more and more positive, and over here I see very positive slope, less positive slope, almost 0 slope, and back to 0. So there we go. What about here? Well, again, we start with the 0 slopes, and then I'm going to say I have positive as it gets, less positive, back to 0. And here, a little negative, more negative, more negative. Now what I don't know is this like a negative x to the third, or am I looking at something like a sine graph? Can't quite tell. If it's a sine graph, we know that the derivative would be cosine. But if it's a third degree polynomial with a negative leading coefficient, well, then I would be thinking about a negative x squared. So I'm just going to be a little vague about it. I have a negative slope that heads to 0, and I have a little negative and more negative. And I'm going to stop like that, because I don't know. All right, here, 0 slope, 0 slope, a little positive, more positive, that's about as positive as it gets, and then less positive, smooth curve, a little negative, more negative, that's very negative, now we get less negative. And over here, very negative, less negative, almost 0, back to 0. Wow, you know, when I graph these 0 slopes and then think about just sections of the graph, this isn't so bad. Here, for example, I see a little negative, more negative, very negative. From here to here, I see only positive slopes, a little positive, more positive, that's about as positive as we get, and then less positive. And here, very negative slope, less negative, almost 0. And so I'm looking at something like that. And again, I see, look, if this is a negative third degree polynomial, my derivative will be some kind of negative second degree polynomial. All right, what about that one? Well, I think that's a 0 slope there, and I think that's a 0 slope there. And so I have slightly positive, I have most negative back to 0, I have a little positive, very positive, less positive, but I don't actually get back to 0. Alright, flat spot, that's a 0 slope. There's another 0 slope. Hey, have you figured out about multiplicity yet? Well, let's take a look. Very negative, less negative, almost 0, 0, less negative, more negative, more negative. So look, I had a 3rd degree wiggle turned into a 2nd degree bounce. I'm supposed to be back at 0. Where was I going? I guess I was too busy bouncing. And these are all positive slopes. So, this goes down 1 degree. So instead of bouncing, we pass straight through. This 3rd degree wiggle goes down 1 degree and becomes a 2nd degree bounce. Okay, I think that's a 0 slope there and a 0 slope there. Negative, less negative, back to 0. And these are all negative slopes. And this is very positive, less positive, gets to 0. Okay, my 3rd degree wiggle becomes a 2nd degree bounce. My 2nd degree bounce becomes a pass through. Sketch a smooth curve whose graph is both everywhere positive and increasing gradually. Okay, so I want to talk about a place with a smooth curve where the slope, not the function, the slope is positive and increasing. Okay, so what does that mean? Well, a positive slope means function is increasing. And if the slopes are increasing, am I increasing this way or am I increasing this way? Which of these pictures shows f is increasing because the slopes of f are positive, and those slopes themselves are increasing? Well, here I have a very, very positive slope, but this is less positive and even less positive. My slopes are supposed to be getting bigger and bigger. Like here, this is very positive slope. These are less positive. So, my graph looks like that. Okay. Sketch a smooth curve whose slope is both positive everywhere and decreasing. So it's not the function that's decreasing. Slope positive, slope decreasing. So what's happening on the regular function? We know positive slopes means increasing. This was positive slopes and increasing slopes. Now I want positive slopes and decreasing slopes. So slopes positive means f is increasing. Slopes decreasing means whatever my slope was here, my slope over here has to be less, and my slope over here has to be even less. Okay, so that's the shape for B. Now what about C? Sketch a smooth curve whose slope is both everywhere negative and increasing gradually, becoming less and less negative. Okay, so slope is negative and increasing. So a negative slope means the function is decreasing. So am I decreasing this way or am I decreasing this way? Where do I see my slopes getting less and less negative? Well, here I have more negative, even more negative. Here I have very negative, less negative, less negative. So I think that's my picture. Decreasing and concave up. And finally, we're looking for sketch everywhere the slopes are negative and decreasing. Slopes negative, and slopes decreasing. And that's going to be this. The slopes are all negative because the function, I see the function is decreasing. And what's happening to my slopes? Well, 0, -1, -2, -3. The slopes are getting smaller and smaller. The slopes are decreasing. Okay. And this may be in line with what you remember we did about drawing that graph when we knew about whether the function was increasing or decreasing and contour up and contour down. And so remember, it's really only 4 shapes we're talking about. This is f is increasing and contour down. This is f is increasing and contour up. This is f is decreasing and contour down. This is f is decreasing and contour up. It's just that we have a lot of ways to talk about these 4 shapes. So in the last problem, we described this as the slopes are positive and decreasing. This is very positive slope, less positive slope, almost 0. My slopes are getting smaller. They're all positive, they're just getting smaller. And here we said slopes are positive and increasing. I start off with a 0 slope, a slope of 1, a slope of 2, a slope of 5. Here, slopes are negative. You see a decreasing function. That tells me slopes are negative there. And what do we know about those slopes? Well, that's almost 0. That's -1, -2, -10. The slopes are decreasing. And finally here, I have that the slopes are negative and increasing because I go from very negative to less negative to almost 0 to 0. All right, now 11. 11 says, given the numerical values in the table, approximate values for the derivative at each given x. Where is the rate of change positive? Where is the rate of change negative? And where does the rate of change seem to be the greatest? Okay, so we've got this table, 0, 1, 2, 3, 5, 6, and I didn't like it. Still remember being traumatized by spacing as a kid. 0, 1, 3, 4, 5, 6, 7, 8. Whew. All right, so we've got f, and we're approximating f prime. Okay, 18, 13, 10, 9, 9, 11, 15, 21, 30. Okay, so they ask us to approximate the value of the derivative at each x. So I actually want to take a look at 1. Because when I look at 1, I see, well, I could do something over here. I could do something over here. Like, I could say 18 minus 13 over 0 minus 1. And that's going to be -5. Or I could say 13 minus 10 over 1 minus 2, and I get -3. So my approximation, my average rate of change over here is -5. My average rate of change over here is -3. And so I'm actually going to go with an average of those two and say -4. Now, if I want to know, approximate the slope over here, I can use this, or I can use this. So what about 10 minus 9 over 2 minus 3? That's 1 over -1, which is -1. So if I average -1 and -4, I have -5 times. Okay? Here we said the slope was, no, let's go back a second. Okay, I'm going to have a workspace, and then I'm going to have an f prime. So over here we said the average rate of change is -5. Here we have -3. Here we have -1. So I'm going to say at this point, -4, I'm going to say at this point, -2. Okay, I like this better. Here, there's no change. And so when I average these, I have -1/2. Here, I go up by 2. And if I average these, I get 1. And here, I'm going up by 4. And when I average these, I have 3. Here, I went up by 6. And I average these, I have 5. And here, I went up by 9. And when I average these, I get 7.5. Now, that's that slope, that's that slope, that's that slope, that's that one. I feel like I'm missing something. I used these two to make that, and these two to make that, these two to make that, these two for that one, and these two. Okay, goes in, goes in, goes in, goes in, goes in, goes in. That's this to this, to this, this to this. There we go. Now what about the endpoints? Well, with the endpoints I can't average. All I can do is use that first slope. So I'm going to have -5 here, and here I'm going to just have 9. Okay, so what do we notice? Well, function is decreasing because of these negative slopes, then the function is increasing. Okay. Does the function increase, is the function, I'm just going to answer the questions here. Where is rate of change in f positive? Rate of change in f greater than 0 on 4 to 8. Okay, and then they ask us, where is it negative? Well, f, rate of change in f is less than 0 on 0 to 3. I don't want to say 4. Okay. No, I don't know. I don't know when we go from negative to positive. Somewhere between 3 and 4. Okay. Where does the rate of change seem to be the greatest? Well, that was my biggest rate of change for that one. And so I'd say at x equals 8, rate of change is the greatest. That's 11. Now, curiously, I didn't renumber, so the back starts with 23. I'm getting the sense that you're okay doing these. Maybe not this one. Maybe not this one. So I'll just do those and let you do the others. So I've got a 0 slope here. Got a 0 slope here. Didn't I do this on the other side? Kinda looks like number 7. So I have positive, but only slightly positive, negative, positive, and then these head back to 0. Okay. And do you remember the derivative of e to the x from our microscope worksheet? I only ask because on the microscope worksheet, you end up at each point with a slope that is the same as the point. So I think these are all positive slopes. This is near 0. This is very positive. And so there's my f prime. Okay, so now here's a graph of f. This is a graph of f. Find out where f is greatest. Well, I think f is greatest at that point because that's the highest y value. So x sub 3. Okay. Find out where f is least. Well, the lowest value of f appears to be here at x sub 4. Find where f prime is greatest. Remember, f prime represents the slopes of f, so I'm looking for when the slopes of f are greatest. I'm looking for the place where the slopes are most positive. Okay, I see a positive slope over here. It's a positive slope here. Which one is steeper? I think this one is steeper. This is less steep, negative, maybe 0. So I'm going with x sub 5. And where's f prime least? Where are my slopes most negative? Well, I think that's a 0 slope, so I'm going to go with x sub 3. Okay. Next, label points A, B, C, D, E, F on the figure 219. Point A on the curve where the derivative is negative. Okay, so look, you've got lots of choices here. You've got negative slopes here, you've got negative slopes here. So the derivative of this function would be negative. I'm just going to pick a random place to stab a point where the slopes are negative. Doesn't have to be there. Could be here, could be here, could be here, could be here. Okay. B, point on the curve where the value of the function is negative. Well, the value of the function is negative only over here. Point C on the curve where the derivative is largest. Where's the most positive slope? I think it's right there. D, point on the curve where the derivative is 0. Well, I got lots of choices here, here, or here. How about this one here? And E and F are different points on the curve where the derivative is about the same. Well, I see this and this kind of look the same. Or you could say here and here, but that's a little harder to see. So I'm going to go with E and F. Okay, and do we need 220? No, we don't need 220. That's for a different problem. We're only using 219. So the last problem say that we're supposed to find the derivative in each case using the limit definition of the derivative, no shortcuts. All right. So here we go, 13. We've got g of t equals 3t squared plus 5t at t equals 1. So I want g prime of 1, which will be the limit as t heads to 1 of, I'm going to use this one, g of t minus g of 1 over t minus 1. So that's going to be the limit as t heads to 1 of 3t squared plus 5t minus g of 1. g of 1 is 8, because I plugged a 1 in for each of those t's, over t minus 1. All right, so now what can I do? Well, I can say that g prime of 1 equals the limit as t approaches 1 of t minus 1, 8, no, we're at 8, plus over t minus 1. These cancel. I can plug in my 1. I get 11. G prime of 1 is 11. All right, so that's that limit definition. And now we'll use another limit definition of derivative, just so that we practice. So now we're looking for f, this is problem 14, f prime of 10. And so I'm going to find f prime of 10 by doing a limit as h heads to 0 of f of 10 plus h. So I've got 10 plus h squared, don't lose the 5, minus 10 squared. So I'm using the limit as h heads to 0 of f of a plus h minus f of a over h. This is the limit definition of the derivative that I'm using. Okay, so that's over h. There's a 5. Don't forget the 5. Okay, so then f prime of 10 is going to be the as h heads to 0 of 5 times 100 plus 20h plus h squared minus 100 over h. And so that's going to be the limit as h heads to 0, 500 plus 100h plus 5h squared minus 500 over h. And when we combine like terms, those go away. And I notice I can take an h out of everything. So f prime of 10 is going to be the limit as h heads to 0 of 100h, no, I took that an h, plus 5h. Actually, I want to show that h, 100 plus 5h over h. And so now I have the limit as h heads to 0 of 100 plus 5h, which is 100. So f prime of 10 is 100. Okay. Now we can confirm this work by saying, okay, if y equals 5t squared, then y prime is 10t. And if I want y prime of 10, that's 10 times my input of 10. That's where the number comes from. But we're not using shortcuts here, we're using limit definition of the derivative. You're more than welcome, and in fact strongly encouraged, to check your work with your derivative shortcut, but you have to use the limit definition of the derivative. 15. 15 says f of x equals x to the third at x equals negative 2. Okay, well let's find the general derivative. X equals h heads to 0 of f of x plus h minus f of x over h. So f prime of x for us is going to be the limit as h heads to 0 of x plus h to the third minus x to the third over h. Hopefully you remember your binomial expansion. I know because of COVID, we didn't get to binomial expansion in chapter 1 this past spring, so you have to remember number 2. Limit is h heads to 0, x to the third plus 3x squared h plus 3x h squared plus h to the third minus x to the third over h. How did I do that? Well, I did the binomial expansion. If I had to go the long way, I'd FOIL these out and have x squared plus 2xh plus h squared. And then I would distribute an x plus h into those. So I have x to the third plus 2x squared h plus x h squared, and then distribute the h plus x squared h plus 2x h squared plus h to the third. And notice I have 2 of these plus 1 of them, that makes 3 of them, and 1 of them plus 2 of them, that makes 3 of them. Okay? So let's talk about simplifying this expression. We now get the limit as h heads to 0. These cancel. I can pull h out of everything on top. 3x squared plus 3x h plus h squared over h. I can cancel out an h from top and bottom, and at this point I can do my direct substitution. If I had plugged in 0 for h here or here, those would have given me 0 over 0 situations. I have to manipulate this algebraically enough until I can plug in that value with direct substitution and don't get 0 over 0. So what do I have here? Well, when I plug in a 0 here, this goes away, and I plug in a 0 here, this goes away. And so I know that f prime of x equals 3x squared. We knew that from our shortcut, didn't we? The derivative of this, bring down the 3, subtract 1, and there we go. And we're looking for f prime of negative 2, which will be 3 times negative 2 squared, or 12. All right, there's 15. 16. 16 says x to the third plus 5. All right, so let's use another limit definition of the derivative. We'll go back to the first one we used. x approaches 5 of f of x, which is x to the third plus 5 minus f of 5. That's 125 plus 5 is 130 over x minus 5. Well, I know that x heads to 5. This is going to be x to the third minus 125 over x minus 5. And luckily, you spent enough time in Algebra 2 and pre-calc factoring sums and difference of cubes that you haven't forgotten this. Hey, if you forgot this, you kind of need that knowledge. You might want to go back and review some factoring. This is going to be x minus 5 times x squared plus 5x plus 25 over x minus 5. These cancel, and now I can plug 5 in for all the x's. That's going to give me 5 squared plus 5 times 5 plus 25, and that's 25 plus 25 plus 25, or 75, is f prime of 5. All right. Next, we've got 1 over x. F of x equals 1 over x, and x equals 2. So, how about f prime of 2 equals, and I'm going to use the limit as h heads to 0 of f of a plus h minus f of a all over h. So our a value is 2. So this is now going to be the limit as h heads to 0 of 1 over 2 plus h minus 1 over 2 all over h. Okay, let's make a common denominator up top. So I have to multiply by 2 over 2 and by 2 plus h over 2 plus h. So what do we now have? We've got f prime of 2 equals the limit as h heads to 0 of 2 minus parentheses 2 plus h over 2 times 2 plus h over h over 1. So I'm going to, do the flip and multiply thing to save some space. H over 1 becomes 1 over h. Alright, so I distribute the negative, and I end up with the limit as h heads to 0 of negative h, 2 times 2 plus h times h. Well, these can cancel, and so I have the limit as h heads to 0 of negative 1 over 2 plus h. Now I can plug in that 0 for h, and I get that f prime of 2 is negative 1/4. Does that make sense with our shortcut? Well, remember that f of x is x to the negative 1, and so f prime is going to be negative 1 x to the minus 2, or negative 1 over x squared. And that's what we had here, negative 1 over that x value being squared. So yeah, I feel good about this. Okay, that one was 17, and now the last one, 18. 18. And the function here is g of z. G of z equals z to the negative 2, and we want g prime of 2. Alright, so I guess I'm supposed to use the general derivative now, so g prime of z is going to be the limit as h heads to 0 of z plus h to the negative 2 minus z to the negative 2 all over h. Weird. Well, I wish I'd used a different definition of the derivative. But let's see this one through. 1 over z plus h squared minus 1 over z squared all over h. So I need to make a common denominator. I'm going to multiply here by z squared over z squared, and here by z plus h squared over z plus plus h squared. So what's my limit look like now? Well, still the limit as h approaches 0 of z squared minus z plus h squared over z squared z plus h squared. And remember how this is all divided by h, so I flip and multiply and have 1 over h here. Okay, if I plug in 0 now, I have z squared minus z squared on top, and I have a 0 on the bottom. So, yeah, no, that's not going to be good. I need to take this further. So, I think we're going to have to do some foiling. So now we're going to have g prime of z equals the limit as h heads to 0, z squared minus z squared plus 2zh plus h squared over z squared times z plus h squared times h. Okay, don't forget to distribute this to each of those. So your next step is going to be g prime of z equals the limit as h heads to 0, z squared minus 2zh minus h squared over z squared z plus h squared times h. These cancel. I can take an h out of the top. G prime of z equals the limit as h heads to 0, h, I'm going to take negative h, and have 2z plus h here. I've got h on the bottom, z squared on the bottom, z plus h squared on the bottom. So I can cancel out these. Now I think it's safe to plug in h equals 0. So this goes away, and this goes away. And so what do we have? We have 2z over z to the 4th, or 2 over z to the 3rd. So g prime of z is 2 over z to the 3rd, and we want g prime of 2, so that's 2 over 2 to the 3rd, 2 over 8, or 1/4. All right, we reviewed our limit definitions of the derivative. I hope this worksheet was helpful to you, and I'll see you in the next one. Take care.